Christian Böhning from Warwick. Will present us a survey of some principal approaches to the problem of stable irrationality, very general cubic hypersurface. Christian?
Yeah, thank you very much for the invitation and the opportunity to talk in this framework. So yeah, I want to use the first of my two talks to give a survey of some approaches to this problem of irrationality of cubic hypersurfaces, and it will be a very biased survey, meaning that I will emphasize approaches that I've made myself some contributions to, so I apologize for that in advance. Also, of course, this has all the disadvantages and advantages of a survey talk. So the disadvantages being that it may be scarce on details and touch on a lot of, well, somewhat unrelated topics in the course of the talk, but it may be advantageous if, well, to see all of these different approaches laid out in front of you in conjunction, so we can see where they fail and maybe learn something from it. And I also try to point out open ends and some possible loopholes or places where I still see some leeway to make further progress or to develop that further. So I'll talk about three groups of approaches. So first being finding, say, useful analogs, useful higher dimensional analogs of the intermediate Jacobian. For threefolds. And the second, well, I'll say a little bit about birational automorphism groups. So these are all very well-known techniques to prove irrationality for various classes of rationally connected threefolds. So certainly this Noether-Iskowski-Marni method was quite successful, also in higher dimensions, to rational rigidity and establish irrationality in various situations. So I'll say some words, very few words about birational automorphism groups of cubics. And then lastly, I want to say something about the degeneration technique or degeneration techniques and further developments of degeneration techniques in directions that may potentially allow one to make some progress on the problem of stable irrationality for cubics. So this would be an approach that always has to be paired with kind of obstructions to Chow zero universal triviality. Of smooth projective varieties, such as, say, the Brauer group or high unramified cohomology groups or differential forms and positive characteristics, such things like that. Now, was to start with, so let me start with some very old but still very relevant material. So what does one do for cubic threefolds? So this Clemens and Griffiths. So generally for rationally connected threefolds, say one looks at, well, the integral polarized Hodge structure on their middle cohomology. Yes, and so one has this integral H3V mod Z modulo torsion in there. And so one associates to that integral polarized Hodge structure a principally polarized abelian variety, so this intermediate Jacobian, so we get this intermediate Jacobian from that set up. Yes. Oops. And that comes with this datum of an ample divisor, yeah, this well defined up to translation, so giving this principal polarization, which is very important, yes, and to consider this abelian variety together with this polarization datum. And so then, as you all will be very well aware, so Clemens and Griffiths essentially proved that if V is rational, then this intermediate Jacobian as a principal polarized abelian variety is isomorphic to a product of Jacobians of curves. Yes, and well, the proof, of course, is also very well known to all of you. So, well, what one does once that P is rational and when it resolves the indeterminacies of such a rational map from P3 onto V, and one looks at this roof to conclude, and one uses two very important properties of principal polarized abelian varieties that I want to point out, because those are exactly the ones that well have been very hard to replicate in other contexts. So they have these properties that any principally polarized variety admits a unique decomposition. So after reordering the factors, a unique decomposition as a product of indecomposable principally polarized abelian varieties. Yes, and moreover, Jacobians of curves are indecomposable. So, so principally polarized abelian variety, A, say with polarizing divisor theta, is indecomposable if and only if this theta is irreducible. So Jacobians of curves are indecomposable. Yes, of course, then you also need to know more facts about Jacobians of curves eventually to conclude. But so these are really two properties that I want to emphasize because, well, I like to think of them as somewhat being analogous to some unique prime factorization holding for principally polarized abelian varieties. So, these are some good properties, somewhat reminiscent of unique prime factorization. And so I want to say that, so the primary problem in other contexts, well, at least in my mind, has been that it has been difficult to replicate these good properties of unique prime factorization in other contexts. So I want to talk about two. So one approach that I still well like very much, and that could still be souped up potentially. Well, I'm not sure. Maybe others in the audience will know much better than I do. Is this approach by Kulikov? So this is very natural somehow. So that dates back to 2008, where he proves the following. So instead of, well, this intermediate Jacobian, we can still talk about integral polarized structures also in even dimensions, so for cubic fourfolds, say. And he proves that if the integral polarized Hodge structure on the transcendental lattice of any smooth projective surface is indecomposable, then indeed a very general cubic fourfold is irrational. So the integral polarized Hodge structure on the transcendental lattice of any projective surface being irreducible would imply that's a very general cubic fourfold. So then, well, unfortunately, it turned out so that this was joint work by Auel and von Bothmer and myself. I don't quite remember, so I didn't put it down here. So around 2014 or thereabouts. Actually, this can be false sometimes. So, for example, for the Fermat sextic, we showed explicitly that this integral polarized Hodge structure on the transcendental lattice of that surface decomposes using, well, basically a lot of previous work by Loyengra. So the Fermat sextic. So this, well, the assumption is false. But yes, so notwithstanding that, I think it's still a very attractive point of view on this whole topic. Some underlying the Hodge, lots of Hodge theoretic approaches to this problem, and I want to point out that so I'm not aware that this is known. So if one could prove that the set of isomorphism classes of smooth projective surfaces with integral polarized Hodge structures on their transcendental lattice decompose was countable, then irrationality of a very general cubic fourfold would still follow. So if the set, so somehow if one could prove that this cannot happen in, say, families or something like that, yeah. So if the set of isomorphism classes, smooth projective surfaces, so with integral polarized Hodge structure on transcendental lattices decomposable is finite. So one can still conclude, yeah. So one can still conclude rationality of very general cubic fourfolds. Yes, so this is something that I think is open, maybe. So I'm not aware of any counterexamples, though it may well be that this does indeed happen more generally, this decomposability. So to leave this and say one, so touch on one other approach that aims at generalizing this concept of intermediate Jacobian to other setups. So this is also a very active approach, primarily due to Kuznetsov. So I'll just say some, this has also been developed further, I understand, recently. So I'll just say something about the initial approach. So the idea is that also instead of with, so this is a very rough idea, that instead of with principally polarized abelian varieties, one could instead try and work with pieces in semi-orthogonal decompositions in derived categories of varieties. So so one can try to work with pieces in, let me abbreviate, semi-orthogonal decompositions in derived categories of varieties. And in particular, so one can try to single out in certain cases some component that would be analogous to the intermediate Jacobian, so the so-called Clemens-Griffiths component of one given semi-orthogonal decomposition or maximal semi-orthogonal decomposition in some derived category of a smooth projective variety, where one collects all the summons or all the pieces, or one rather throws away all the pieces analogous to Jacobians of curves, which are those that can be fully faithfully embedded into derived categories of smooth projective varieties of dimension at least 2 less than the variety one started with. And well, the catch here is the one issue that somehow handed out by many people. So one issue here is, yeah, so somehow you notice, so in Kulikov's approach, somehow this, the property of Jacobians, that they are indecomposable, fail. The analog of that property here, somehow the unicity of the decomposition of principally polarized abelian varieties into indecomposable pieces fails. So one issue here is So the pieces in, let me say, maximal semi-orthogonal decompositions, so the indecomposable pieces are not necessarily unique. Say up to reordering and equivalence of categories. So, so that means there can be essentially different maximal semi-orthogonal decompositions. So where the indecomposable pieces in the two of them cannot be matched up to correspond to each other, up to reordering and this equivalence of categories. And so that phenomenon was noted, I think, well, that was 2014. So so van Bothmer, Sosna, and myself gave some examples, and also Kuznetsov gave much easier examples in the same period, and then lots of other examples of the same type emerged. And well, it's apparently still not entirely clear. I mean, maybe the experts know more how far-reaching this non-unicity of maximal semi-orthogonal decompositions is. So it's of course it's conceivable that you could, in some situations, always single out some pieces of maximal semi-orthogonal, of all maximal semi-orthogonal decompositions on a given variety that have some specific properties, maybe some Calabi-Yau categories of some sort that have to show up in every semi-orthogonal decomposition whatsoever. That would be one possibility. So there are several, well, workarounds maybe. So this is still a very interesting, inspirational approach. But there is this basic catch somehow here. Also, I want to mention that this is somewhat reminiscent of the fact that if you forget polarizations of principal polarized abelian varieties, then the decompositions there are no longer unique. So somehow, so what I find myself thinking of when I saw this first is that, so to say, if you for example, some abelian surfaces that can be decomposed into the product of elliptic curves in many ways, if you don't remember any polarization present. So so in other words, initially, what I thought of was that one might remedy this setup by endowing somehow the pieces in these semi-orthogonal decompositions potentially with some extra structure, somewhat analogous to a polarization like stability or something like that. But well, I don't know. There's also this recent envisaged work by Kotsevich, Katsakov, and Pantev, I understand, so still ongoing. So I don't know. There is, well, the possibility that one could soup up this approach to make it work. Endowing the pieces in semi-orthogonal decompositions with some extra structure. Okay, so this is what I want to say about this first group of approaches. So let me maybe, yes, so it's a good time to come to birational automorphism groups. So, so I don't want to say quite as much about them. So I want to point out a few facts. So how they differ either conjecturally or could also be known in some cases, how they differ from the birational automorphism group of Pn. First thing I want to point out is that qualitatively, as opposed to quantitatively, the birational automorphism group of a very general cubic and dimensional cubic, say, seems to be, let me say first very imprecisely, and then I'll make it a little more precise. It seems to be very large, and in many respects similar to the n-dimensional Cremona group. So in particular, yes, so for the Cremona group, one has this result by Hilda Hudson and also by Pan that it's not countably generated, or next, besides projectivities, so from 3 onwards, dimension 3 onwards, you certainly need, well, countably many, even algebraic families of generators to generate it. And somehow a similar phenomenon occurs for the birational automorphism group of 4 cubic n-folds. So for example, Jérémy Blanc and Bami in 2015 proved that so the group of birational self-maps of a smooth cubic threefold, any smooth cubic threefold contains elements. So it contains elements contracting surfaces that are birational to any given ruled surface. So you can contract any ruled surface birationally. So it contains elements contracting surfaces birational to any given ruled surface. So this also shows that these groups are very large and very much not countably generated in any sense of the word. But so secondly, what I want to say about them is, so there are differences in the structure of in the structure of algebraic subgroups. So there are some differences in the structure of algebraic subgroups in the 2 cases of Pn and an n-dimensional cubic. So this is, well, of course, this is known in dimension 3, but it's conjectural in higher dimension, because in dimension 3, of course, the result uses Clemens-Griffiths' proof of irrationality for cubic threefolds. So one has that the birational automorphism group of a smooth cubic threefold, well, does not contain any connected algebraic subgroups of positive dimension. So whereas, of course, one group contains many such subgroups. So this does not contain any, say, connected algebraic subgroups of positive dimension. Well, and the simple reason is that if this was the case, it would also contain eventually, well, it would contain either some copy of GM, the multiplicative, or the additive group, and you can get a contradiction from that, because if it did, then you can find some birational model of a cubic threefold on which these act morphically, and you could realize such a cubic birationally as a GM or GA principal bundle over some unirational, hence rational surface. So, and these would of course be Zariski locally trivial, since these are special groups. So then such a cubic would actually be rational, which it isn't by Clemens and Griffiths. So this uses Clemens-Griffiths proof, and so similarly, for example, we would not expect that the birational automorphism group of a very general cubic fourfold contains any copy of something like C star square, such a torus. But it seems hard to use this for irrationality proofs in dimensions, because we don't know how to make use of this assumption, such existence of algebraic subgroups. So that doesn't seem to entail anything for the geometry of the cubics that we could use to get a contradiction. And there's a third thing I want to point out here. Yes, so about birational automorphism groups very briefly. So this is work I did with von Bothmer and Sosna, well, in the period somewhere 2016 up to 2018, say thereabouts. So we did quite a few computations with the for different birational automorphisms of cubics of the so-called dynamical degrees. So I want to say that whereas these birational automorphism groups, yes, are generally qualitatively very large, ugly and unwieldy, and certainly cubics are very far from being birationally rigid, still I think that there will ultimately quantitative differences in these groups, and they can, so I want to say there are conjectural quantitative differences in the so-called dynamical spectra of a very general cubic n-fold, NP4 and NPN, sorry. So what are these? So just very briefly, what you can do is you can associate any birational automorphism of a smooth projective n-fold in an n tuple, or actually it's the relevant information is just an n-1 tuple of real numbers. So this is an R, and -1 called the dynamical degrees of that F, the dynamical degrees. So these are certain entropy invariants, or they are invariants that refine the Gromov entropy of that F. And they've extensively been studied by Blanc and Cantat and Lamy and et cetera. And if F ranges over the entire birational automorphism group of that n-fold, then you can look at the totality of all tuples of dynamical degrees you get in this way, and you call that thing the dynamical spectrum of your. So it's a certain subset of Rn-1. And well, we have quite a few conjectures about well, how subset of Rn-1 could, in the case of a very general cubic fourfold at least, be much more restricted or subject to more stringent restrictions than the dynamical spectrum of P4, which is natural because we would think of the Cremona group somehow as being the wildest birational automorphism group, maybe among all n-folds. This displays the greatest variability somehow. In particular, yeah, so maybe I won't say much more about this. So in particular, for fourfolds, we conjecture that, so you can't have lambda 2, so you can't have this behavior that lambda 2 is much larger than lambda 1 and lambda 3, so you can't have behavior like this or such roofs. So let me just maybe skip this and just say that, so this is something that you can use to quantitatively describe differences between the birational automorphism groups. But the problems that runs into are that we cannot conclude from the presence of a birational automorphism with a funny tuple of dynamical degrees that the geometry on, say, a cubic n-fold or cubic fold is special in any sense of the word, so that we could conclude that such cubics cannot exist. And so some quantitative further development of this Noether-Vygotsky-Manin approach using birational rigidity would be that you start with a certain birational self-map with a certain tuple of dynamical degrees that you know is realizable on P4, and then you prove that if such an F existed on a very general cubic fourfold, then that would have consequences for the geometry of the fourfold, and then you contradiction, say using intersection theory or something, some other geometric information about the fourfold. But so this connection is something that we couldn't yet make. So this is also so far not useful, therefore, to prove irrationality. So this is what I can say about birational automorphism groups, very hazy. Well, everything is an open problem, so so that's in the nature of the matter. Let me say a few words about the degeneration method, so how we could possibly still use the degeneration method due to Voisin and further developments here to make progress on this irrationality problem for cubics. And so I'll assume some familiarity with the basics of that method. And I want to consider for definiteness, say, the stable irrationality problem for cubic threefolds. So just to ease you into the discussion and to make my point why well, looking at this, we were led to some, well, interesting mathematics eventually, though not to prove stable irrationality for cubic threefolds. Well, of course, some people may say that, well, you have no chance, or you stand no chance at all to prove stable irrationality or rationality of cubics using this degeneration method, because, well, nodal cubics are rational. So, but that doesn't really, well, that is certainly an unpleasant fact, but it has not been a totally, absolutely devastating argument against this in my mind, because, well, certainly it's true that if you degenerate cubic hypersurfaces, if you try to degenerate cubic hypersurfaces to something that's also a cubic, so if you look at it, embedded degenerations of cubics to some other type of more singular cubic, then certainly this can never work. So the degeneration method can then never give you something so in the central fiber, that you can use to conclude stable irrationality of a very general fiber of the family, simply because you could also specialize nodal cubics that are rational to this central singular cubic, and then the same method would give the contradictory conclusion that these nodal cubics, a very general one of these nodal cubics, would also have to be non-stably rational, which is nonsense. So certainly you cannot degenerate these cubics as cubics, but if you pass to some other types of birational models, then it is quite possible that you can degenerate those other types of birational models of the cubics to some central fiber that is no longer birational to any cubic itself, and it could also be such that it's not a limit of any family of rational nodal cubics either. So it's just something genuinely different that you get as a limit. So I don't see why this shouldn't be the case. Let me try to point out what happens if you look at them as conic bundles. So these cubic threefolds. So such a cubic threefold is birational. To a conic bundle over P2. With quintic discriminant. or maybe y. So with quintic discriminant. So this quintic discriminant is a very small degree discriminant, and so let me point out why that spells trouble. So well, the issue is this. So if you want to apply the degeneration method and want to degenerate this as a conic bundle to some other conic bundle over P2, and you want to use the Brauer group as a natural obstruction to, say, Chow zero universal reality over the singularization of the central fiber, then there's a basic problem. So, so if you work over an algebraically closed ground field, so you could also degenerate, you could look at unequal characteristic degenerations. Yes, you could degenerate into some positive characteristic. But if you look at an algebraically closed field of characteristic not 2, then you have this Bloch-August type exact sequence, or maybe it's called the Gersten complex, I never know. So one has, so this Bloch-August exact sequence here on P2, so one has, so the unramified Brauer group of P2 is 0, then one has the Brauer group of this function field of P2, the 2 torsion in it. So conic bundles define classes in there. And then one has this residue homomorphism that measures, well, the ramification of the conic bundle that gives a class in this first group. So this has target, so that in the direct sum taken over all curves in P2 of the H1 KC Z mod 2, say, which by Kummer theory you can just identify with the function field of that curve and the invertible elements in their modulo squares. So this is Kummer theory, yes. And so in other words, so in the geometrically simple case where you have a conic bundle over P2 that has discriminant a bunch of curves and is such that the general fiber over a point of each of these curves is a cross of lines, where then this conic bundle induces natural double covers over each of these discriminant curves, and so this delta just associates to the class of that conic bundle, so the tuple, so the tuple of these double covers, or the 2 Galois extensions of the function fields of each of these discriminant curves. And then you have a further map here, say del prom, if you want, so that measures secondary ramification of these covers, and it goes to a direct sum over all points in P2 points, and here you just have, if I ignore theta, is just, you get a copy of Z mod 2 there. And well, if you have a smooth curve, it just works like this. You take a function well-defined on that curve, non-zero function, well-defined modulo squares, and you look at a point on that curve and you just associate the order of 0 pole to that rational function modulo 2, which gives you this. So in particular, what I want to say is that you have this in characteristic not 2, and you can associate to every conic bundle a discriminant profile, what I want to call a discriminant profile. So hence to any conic bundle over P2, you can associate a discriminant profile. And this discriminant profile is just, so this del of the Brauer class of the conic bundle. So it's just an element in this direct sum, all curves in P2 of these H1s. So in other words, I just remember the double covers the conic bundle induces on this discriminant components and take these corresponding classes here. So that's what I want to call the discriminant profile. And then, well, I can say what you would have to do to get stable irrationality of a very general cubic threefold if you chose to view it as a conic bundle and chose to degenerate it as a conic bundle to some other conic bundle over P2, hoping it would be one acquiring a non-trivial Brauer class. So, so to get, say, stable irrationality, let me write that, of a very general cubic threefold by degenerating the conic bundle Y over P2 associated to it to one having non-trivial unramified Brauer group, unramified Brauer group, you would have to achieve the following. You would need that the discriminant profile of the conic bundle you degenerate to decomposes into the discriminant profiles of two non-trivial conic bundles over P2 separately, such that there's no secondary ramification in the intersection of a curve from one profile and a curve from the other profile. So let me just write that. So you would have to degenerate to a conic bundle, say, whose discriminant profile decomposes into the discriminant profiles of two non-trivial conic bundles. So by this I mean conic bundles with non-trivial Brauer classes, such that there is no secondary ramification in the intersection of a curve from one profile and a curve from the other. So this follows staring at this sequence and so this is a formula for the unramified Brauer group that you can develop starting from that sequence, and where you see then where the problem is with quintics. So with quintics the problem is that if you degenerate the quintic, you always have to split off one component that is a P1. So since the discriminant of this conic bundle, this conic bundle is a quintic, well, there are two things that happen. It always splits. So it always splits off. Something isomorphic to P1, yeah, either a conic or a line, yeah, just by degree reasons, and the other catch is that a non-trivial class, so a non-trivial class alpha, say in H1 K of P1 Z mod 2, so in this just Galois homology, this always has secondary ramification in at least 2 points. And you can work out the combinatorics starting from there. and find that there's just simply no way to decompose a quintic discriminant into somehow components carrying well, non-trivial double covers on them, such that you can then separate these into two sets, each of which is the discriminant profile of some non-trivial conic bundle in its own right, and such that there's no secondary ramification in the intersection. So this comes from these two facts. But now, so what we hoped, and which is still some little loophole, though maybe not everyone is overly enthusiastic, and neither am I, but it led to some interesting mathematics at least. So we degenerate into characteristic 2. Because then you see the good thing is, at least we are rid of this Kummer theory, so double covers are now governed by Artin-Schreier theory. There exist Artin-Schreier covers of P1 with ramification in just one point. So this problem with these 2 points disappears. And also Bloch-August theory no longer works the same way. This exact sequence here is no longer there, we found. So that could give us more freedom. So degenerate into characteristic 2. So this is something we did. This, of course, runs into all sorts of technical obstacles and that one has to overcome. Especially the theory of residue maps is different. So residue maps are not everywhere defined, but there is a fix to this using ideas by Merkurjev. But I mean, I just want to point out that Bloch-August theory no longer works as before. Yeah. So so there might be more freedom. Could be more freedom for possible discriminant profiles of conic bundles to exist, and also there exist Artin-Schreier double covers. Of P1 ramified in just one point. So what I then initially had dreamed about, so was, could one degenerate, could one possibly generate a quintic into the following union of two discriminant profiles, to take such an intersection of two lines in P2, and suppose you can achieve that on each of them, you get a non-Artin-Schreier double cover, maybe the same one, and both of them are ramified in this intersection point of the two lines. And then apart from that, you get a smooth cubic here, elliptic curve, and some non-trivial Étale double cover on it. So could one cook up a conic bundle with such a discriminant profile in characteristic 2? So you see there would be no secondary ramification in the intersections. So then if there were conic bundles having these two discriminant profiles, this cubic and this cross of lines separately, we would be done, or we would be through. However, of course, nature doesn't want to yield. So there's another catch now. So this would be nice. So there's this combinatorial possibility in characteristic 2. However, some proof, so this is work with Auel and a PhD student of mine, Picazzi, who finished this year, and von Bothmer. So we did that from 2018, well, maybe 2019, something like this. So one can prove the following. So first of all, there are no conic bundles over P2 in characteristic whatsoever with discriminant profile that can even locally look like such two smooth branches here crossing transversely, and with a double line, the fiber of the conic bundle above this point here, the intersection point, and a cross of lines being the fiber outside. So this is just because the universal discriminant somehow for conic bundles, well, for conic bundles in characteristic 2 is 2 singular. So unfortunately, so there are no conic bundles. There are no conic bundles over P2 with discriminant profiles, or with discriminant profiles that, or with discriminants that locally have the form. So even état locally, two smooth branches crossing transversely, and then here over the point here outside, the fiber of the conic bundle being a cross of lines, and here over this point a double line. And so such a thing does not exist in characteristic 2. Instead, what does exist is, well, so instead, so what you get, so this local behavior that I draw for you now exists, funnily. So you can have a conic bundle that has discriminant 3 lines passing through a point in characteristic 2, and one and the same Artin-Schreier double cover on each of them, so isomorphic Artin-Schreier double covers on each of them, all ramifying in this one point. So this is also, so this is very strange. So here, so this somehow exists, what I just said. And so looking back at this Bloch-August exact sequence that you have in characteristic not 2, you also see that such a thing cannot exist. Here the ramification, this secondary ramification here, however you want to quantify, it doesn't add up to 0 in this point. So some of this is very weird. But I want to say that we used this whole theory to produce new examples, or new examples of conic bundles, threefold conic bundles over P2 with sextic discriminants in characteristic 0, so defined over Q, that are not stably rational. So now, of course, the very general such is not stably rational. But this is not what I'm talking about. What I'm talking about is that we can write down explicit special conic bundles over having sextic discriminants. They're not very general, they are very special, having explicit equations, and we can show they are not stably rational, applying this theory, reducing to characteristic 2, and in these cases, no other method can be used to prove that they are not stably rational. Discriminants only become reducible in characteristic 2, and there are no other methods either that one can use, as far as I can see. So that's a nice application as some some entertaining application. Yeah. So, but what is still open? So here is still open. So I don't know the answer to this. So I don't know if there is a conic bundle in characteristic 2 over P2 with quintic discriminant and non-trivial unramified Brauer group. So this I don't know. In characteristic 2 and non-trivial unramified Brauer group. So I don't know. And well, probably not, but you could then consider other situations where maybe the conic bundle induces inseparable double covers over some of the discriminant components, and we haven't looked at such things yet. Or you could also think about degenerating to some wild conic bundles a la Mori. So it could be that the total space maybe of such a conic bundle is smooth, but the geometric generic fiber is not. So there are other scenarios that one could look at. And we also don't know, so this is somewhat related to this problem. So what discriminant profiles are possible for conic bundles in characteristic 2? So this we don't know. So by this, I mean, how can you look at, so how can you tell by looking at a given discriminant profile that it's realizable by some constant over P2? For example, you can use this Bloch-August theory to answer that question in characteristic not 2. I don't know how to do it in characteristic 2. So this is something. So this is one direction one can develop this degeneration method into that yields some new results. And another direction, which now I have unfortunately only maybe 3 minutes to talk about, and well, which may also be a blessing because this is still much under development and not yet in satisfactory form, I feel. So it's this. So that's something we are doing currently. So with Michel van Garrel. So let me just say this in words mainly. A different further development of the degeneration method. So this is something related to prelog or log Chow groups and what we call prelog decompositions of the diagonal. So this is work with, again, von Bothmer and Michel van Garrel. So that's ongoing. We started 2000, maybe there are some preprints, 2019. So here the idea is essentially the following. So let me just very quickly say that. So how's the argument for the degeneration method in the classical setup? So what is Voisin's argument essentially? So you start with a family of varieties, say over some curved tray, and there's a distinguished point O corresponding to a central fiber, and you assume, say, that the general fiber of this family, or every fiber, say, outside of this mark point, is smooth and, say, stably rational or retract rational, even weaker, something like that. Yes, and you want to obtain a contradiction in some cases, yeah, assuming this. And now you're saying if this is the case, well, then at least you can say that passing to possibly some ramified cover of this C, then you get a decomposition of the diagonal in the family, even in the family, in this product family over C prime. And you can specialize this into the central fiber, yes, into the central fiber. You get a decomposition of the diagonal on the central fiber, which is singular, and which can be very singular as we want to, essentially. So then the argument goes in the degeneration method in the classical case, well, we can't really control whether decompositions of the diagonal on such a singular animal exist or not. So we have to assume that this is maybe mildly singular. Well, there are improvements by several authors, but that's the classical setup. We have to assume it's mildly singular, say it has a zero universal trivial desingularization, V naught tilde. And if that's the case, we can say that this V naught tilde inherits the decomposition of the diagonal from V naught. it doesn't disappear, or the property of having one isn't destroyed by passing to this dissingularity. And then on the smooth one, we can use abstractions such as the Brauer group higher unramified classes or differential forms and positive characteristic to obstruct its existence and conclude that our initial assumption was false, that the general fiber of this family was indeed not retract rational or anything of that sort. So the idea here of this project is that one could use much more singular degenerations, even degenerations degenerating into something having many components, even rational components, intersecting in rational varieties, and not pass to any desingularization at all when one works directly with decompositions of the diagonal on this singular central V and tries to obstruct not, well, the existence of a decomposition of the diagonal on this singular V naught, which may very well exist. Well, if all these components are rational, some such decompositions may exist, but to obstruct something that is a souped up version of the decomposition of the diagonal, some sort of log decomposition of the diagonal, which means I want to obstruct that there exist decompositions of the diagonal on the central fiber that arise as limits of decompositions of the diagonal in the family Yeah, so I want to obstruct that there are deformable decompositions of the diagonal on the central fiber. And this leads to this notion of log decompositions and log Chow groups, which we've computed for various classes of examples and also for some degenerations of cubic threefolds. Technically, you always have to make several things strictly semi-stable on the way, and that encodes important information. Well, but we haven't yet proved stable irrationality of cubic threefolds or anything using this. What we can do, we can prove that elliptic curves do not have decomposition of the diagonal simply by degenerating them to such a triangle of lines and applying this theory. Yeah, so let me stop here. Sorry for going over time.
Thank you, Christian. Are there any questions? No? If not, let's thank Christian again. And I guess we will restart at 2 p.m. Miami time. Thank you.